Greetings, this is Artie from Fill in the Blanks Yourself. Anyway, this is our second episode on machine language utilizing the Motorola 6800 processor. And last time we laid some of the groundwork, mostly different number systems, because we're going to be dealing with hexadecimal numbers and a few other details to set up for actually getting into the 6800. So sit back and enjoy. Here's a high-level diagram of the 6800 showing the pins, what they do, and what it looks like on the inside, which gets us that much closer to actually programming this thing. But first, let's look at the pin functions. It's an 8-bit processor and thus has an 8-bit data bus. It's bidirectional. Data can both go out and come in. Well, when you're dealing with memory, you can read memory, arrow pointing in, or write to memory, arrow pointing out. Next we have our 16-bit address bus that allows us access to 65,536 different memory locations, but it's not really memory locations because a processor obviously has peripherals. It has RAM, it has ROM, a serial port or two, a floppy disk controller, a blinking LED, whatever. This gives the address of what hardware it wants to talk to, whether reading it or writing it, and this is the actual data, either coming out or going back in. Then we have a bunch of control lines. Read-write. We have to put a bar over the write because this signal is high when the processor is trying to read, and this signal is low when it's trying to write. And usually this is utilized when you're hooking up to a RAM chip, and this line usually goes to the write chip on the RAM. VMA stands for valid memory access, and this goes high when all of the other lines, data, address, and control lines, are valid. Remember, we're in the real world now. When we look at something on paper, we see nice square waves and signals going up and being valid immediately. But in the real world, that's not the case. We have rise times and fall times on signals. And this signal kind of makes sure that you're synced before actually activating a peripheral. Next, we have two interrupt inputs. IRQ, which stands for interrupt request, and NMI up here, which stands for non-maskable interrupt. What an interrupt does is it's a high priority piece of code that is activated by pulling either of these pins, IRQ or NMI low. The processor will finish whatever it is currently, the instruction it's currently executing, and jump to a fixed location and execute some sort of code that needs to be periodically executed and then returns to where it came from. The IRQ is maskable. What that means is, we're jumping ahead a little bit here, but there's a flag inside the processor, the I or the interrupt mask, and if the interrupt mask is set to 1, an IRQ has no effect. It is essentially blocked, and after resetting the processor, the interrupt flag is set. So you kind of want to wait until the processor has internally initialized itself before you allow interrupts to actually, interrupts are going to occur anyway if they're hardware generated, but you're preventing the processor from receiving them, and it is under your control when you want to allow them by resetting this flag. The other interrupt, the NMI, is the non-maskable interrupt, and that's usually for really high priority stuff. you have a big red button on your hardware, and when you hit that, everything stops because somebody's finger is about to be cut off. You pull the NMI input low, it cannot be masked. It will stop whatever it's doing, whether it's running foreground code or actually already in an interrupt, and again jump to a fixed location and execute a high priority code that is the highest priority in the entire microprocessor. Next we have the reset signal. It's active low, and the way it should work is when you're first applying power to the processor, you need to wait until the power stabilizes. So reset should stay low for a few cycles of the clock till the power stabilizes, then you let it come back up, and then the processor actually starts running. I don't know the exact number of cycles required, but it's clearly documented how long this has to be held low. And usually a simple RC circuit is used that when power is applied, that where the RC time constant is long enough to allow it to wait long enough for the power to become stable. Continuing over here, we have the Dbe signal, which stands for Data Bus Enable, and it's active high, and that discussion, that actually under normal circumstances gets connected to one of the clock inputs, so we'll talk about that when we get to the clocks. There's a halt signal here paired with a BA signal. The halt signal, when pulled low, basically tells the processor to relinquish the bus. It'll go ahead, it'll tri-state everything, it will complete its current instruction, tri-state everything, so that it has no effect on the bus, on anything in the circuitry anymore. And when that procedure is clear, or is completed, it asserts the BA signal, making it go high, and telling whomever did a halt request that the halt request has been processed, and the rest of the bus is now ready to be manipulated by something external, because this guy's going to stay asleep until the halt signal goes back high again. Next we get to the clock signals, phase 1 and phase 2. And phase 1 comes out usually out of a crystal-driven oscillator that has a crystal hooked up to it, some inverters or whatever buffers to condition the signal and make it strong enough to drive things, and usually it's also divided down to be at the proper clock frequency that you want it to be. And phase 1 looks like this. Now phase 2, the 6800 requires a non-overlapping clock, pair of clocks I should say, but non-overlapping means, well, first of all, the clock's out of phase, so phase 2 looks like this. It is high whenever phase 1 is low. The non-overlapping part says that phase 2 should not become active until after phase 1 has become inactive. And the same thing on the rising edge of phase 1. Phase 1 should not rise until phase 2 has become inactive. And that's just the way the processor needs these to work properly, internally work properly. And after looking at that, the only real thing remaining is, well, there's two things remaining. We have the Dbe signal, data bus enable, active high input, and under normal circumstances, Dbe is tied to phase 2. So basically when phase 2 goes high, the data bus gets enabled. Then there's also Tsc Tri-State Control, and that is usually, under normal circumstances, lets you play games with the state of the data bus and the address bus. Somehow it lets you control what we do with the halt and bus available signal, but again, under normal circumstances, it's more of a debugging thing. Under normal circumstances, this is permanently tied high and becomes a non-issue. So now you know what the hardware signals do. And finally, let's look at the programmer's model of the 6800. So these are called registers, and that's just a fancy word for internal memory locations in the processor. We have two accumulators, A and B, and these are 8-bit. And the same thing here. And then we have three 16-bit registers, which are very useful because you can directly manipulate them in the processor. But of course, since they're 16 bits wide, if you need to load or store one of these registers, you actually have to make two reads from memory, because every read can only read 8 bits. And the way this works is whenever you need to read or write an 8-bit address, you do an 8-bit access with the high part of the higher byte of the memory, and then you do a second access with the lower byte of memory. The other two are the stack pointer being used for temporary storage, also for saving the machine state when an interrupt occurs. And the stack is just another part of memory that you have to be very careful with. They are in this machine. There's no security inherent in the architecture of these processors, unlike newer processors now. If you mess up in your code, you can overwrite the stack area and cause havoc with your program, create all sorts of problems. But yes, we will see examples of this. And finally, we have the program counter, which is also 16 bits. And the program counter just points at what the CPU is currently executing. And finally, we have the condition code register, which is also 8 bits wide, but only the 6 lower bits are significant. The upper ones are always set. The bits are always set. If we go through them from right to left, we have the carry flag, and again, we will demonstrate how all of these work when we actually look at code that's running. The overflow bit, I guess I should mark these. The 0 flag, which indicates, in most cases where the last operation performed resulted in a 0 result. The negative flag. And the negative flag, really, all it does is it looks at the most significant bit. Bit 7 in an 8-bit register, bit 15 in an index register, and the negative flag is basically a copy of that. The I flag, or the interrupt mask, we already talked about. That's simply a mask preventing the IRQ from happening. The H flag, which is the half carry flag, which becomes important when you're doing decimal additions, where in a byte you have, a byte, I don't think I mentioned this last time, 4 bits are called a nibble, and in a byte there are 2 nibbles, lower nibble and upper nibble. And you can usually store 2 digits of a decimal number in a byte if you want to keep everything in the decimal domain. And the half carry flag basically tells you if whatever instruction you did caused a carry or borrow from the lower nibble. And that pretty much sums up the overview. And now, drum roll please, here is your very own first Motorola 6800 machine code program. And let's go over what that actually means. Obviously these are all hand-drawn, handwritten I should say, but the first column is the memory location of where each instruction sits. The second column is called, well, it's one step before machine code or machine language. This is assembly language. Assembly language is used to actually write the programs, make it a little bit more human readable, but the CPU can't do anything with this. I mean, if we dumped all these ASCII characters into the CPU, it wouldn't do a whole lot. So what we need for the CPU to work is that's when we come to the actual machine language. So this is the machine language that this assembly language would generate. Normally what we use is something called an assembler. You can kind of think of it as a really simplistic compiler, because all the assembler does is it parses the text and then looks it up in a table and figures out what the machine language or machine code for that particular instruction is. Now this is native code. These are bytes that the 6800 can execute directly. And again, there's not a whole lot the processor can do with this, but when you see EPROMs, this is the code they contain, machine code. Now what does this actually do? Oh, and we do have a fourth column, and what the fourth column is telling us here is how many machine cycles does it take to execute, for the processor to execute each instruction. And what a machine cycle is one complete cycle of the phase 1 clock. So the phase 1 clock has to oscillate twice for this instruction to be executed in its entirety. And why would you need these numbers? Well, this is a timing issue. If you've watched the video on the Atari 2600, remember when you're in a horizontal line in the visible part of the screen, you actually have to count cycles to know when to turn on a pixel to create certain shapes. And counting cycles, which I probably didn't explain at the time, is essentially at the beginning of a horizontal line, you basically start counting how many cycles it takes for each instruction. And that's how you would adjust where a pixel would occur or not. But now to what this actually does. We'll start it at memory location 0. And in the assembly language, we have something called a mnemonic. I should probably write that down, because if you never heard that word before, you probably have no idea what I'm saying here, but it's spelled like this. The mnemonic is basically also the opcode that says what the processor is supposed to do. After the mnemonic, we have 0, 1, or 2 operands. And those specify exactly where in memory or what registers this operation should be performed on. In this case, the mnemonic itself specifies that we're loading a value into accumulator A. Remember, we have two accumulators. We have accumulator A and B. So this says, take the constant 4 and load it into the accumulator, the internal 8-bit register called accumulator A. That translates to, and this is all in hexadecimal, 86, which is the opcode, and 04, which is the operand. And that's it. So the stuff really isn't that hard to figure out because of assembly language. The mnemonics in assembly language do make it a lot more human readable than actual machine code itself. But going on, we now get to memory location 2. Why? Because this instruction in its entirety takes 2 bytes. So the processor knows that when it reads a hex 86, that there's one more number following it, performs the instruction, and then increments the program counter by 2. So when I say address here, it's really the, I will use them interchangeably. I mean, when a program is executing, the program counter will be set to an address. And when in order to start this program, we have to set the program counter to 0. When it runs, it knows to fetch the next instruction. And during the fetch, it also knows how many bytes to fetch. It will fetch the first byte, and it will internally decode it and immediately know that there's one more byte for it to fetch. There are several different addressing modes which we'll also get into, but the pound sign in front of the 4 says this is immediate, which means whatever number you put after the pound sign gets loaded into the accumulator. Now also keep in mind that the accumulator is 8 bits wide, so your value over here is limited to be between 0 and 255. And an assembler should spit it out if there's anything else, if there's a value in here that's anything other than 0 to 255. So now we get accumulator A loaded with a 4. Program counter jumps to memory location 2 and fetches the next instruction. We'll see this instruction, the mnemonic, if you haven't guessed it already, says decrement A. So we have a 4 in A, and we decrement it by 1. So after the first time this instruction executes, we have a 3 in the accumulator. It's a single opcode, takes 2 machine cycles, and will advance the program counter to 3 because it only has a single byte over here. Now at this point, we briefly talked about the condition code register. And the condition code register is, so the result of doing an operation on the accumulator doesn't just change the value of the accumulator, but there are flags here that tell us what happened. And as we will see later on, what is very important to us is we jump to the next instruction at 3, and BNE stands for branch on not equal to 0002. $sign means hex address. So if A doesn't go to 0, the 0 flag remains reset in the condition codes. Branch not equal simply checks the 0 flag, performs a branch if the flag is branch not equal if the flag is not set, or doesn't do anything if the flag is set. So these are called conditional jumps. And in this case, A just became 3, so the 0 flag wouldn't be set by this instruction, and the branch is taken actually. So this goes to 3, and then the branch goes straight back to 2 again. Finally, we decrement A. It goes from 4 to 3 to 2 to 1, and finally it goes to 0. When it goes to 0, it sets the 0 flag, the 0 condition code, which means that this branch not equal is not taken. It is ignored because the 0 flag is set. We fall through to location 5, and this is just good programming practice. This is basically an infinite loop. What we're saying here is we have branch means unconditional. It doesn't look at any of the condition flags, and what it does is it just keeps branching back to itself. It's chasing its tail. But the reason you do that is you don't know what the contents of RAM may be after that, and the program may try to execute things, and it'll just keep trying to execute stuff. So it's always a good idea when you have short programs like this, test programs or anything, to have an infinite branch at the very end so the processor doesn't go bananas. And the only other thing you may be wondering about is, so we have a branch here or a branch here, and there's a 16-bit number here. So then how come we only have one operand which can only specify 8 bits of value? And that's because the branch instructions are basically space savers. The number they use is a 2's complement hexadecimal byte. I didn't explain it last time, and I won't explain it here, because the only time you really need to know how 2's complement works is if you're hand assembling stuff, such as I have done here. In most circumstances, you'll be using an assembler, and one of the big conveniences of an assembler is that it will calculate what the 2's complement number is to use to perform the branch. Now in a branch, you don't get something for nothing. You still have a byte operand, which limits how far you can actually jump in the address space. Well, a byte has one of 256 different values. But suffice it to say that when you're using a 2's complement, and I may be slightly off in that, but I think you can go, the branch can specify from the actual branch address -28, a distance of -28 up to a distance of +127. It gets more complicated when you're actually coding these, because a branch isn't taken until the program counter is advanced by 2 and blah blah blah. But suffice it to say, it can, the easiest way to remember is, the easiest way to do this is that you can go ±127 locations back or forward, and you need to use another instruction if you want to jump further. A few other instructions we'll see, and we won't hand assemble them here, but let's take the opposite of load accumulator A, store accumulator A. And this will be, remember this was an immediate mode? Well, we can't store into a constant. So basically we have to use a different addressing mode, and what we can say here, store in, we're going to use direct addressing, which limits you to memory locations from 0 to FF, or 0 to 255. But this would store whatever value is in A into memory location 10. The opposite of decrement A, of course, is increment A. There's a whole bunch of branch instructions that all take their cue from the condition code registers. So you don't have to compare numbers or anything like that, but most of these instructions set the condition codes so you can take a conditional jump right after you perform them. And of course the other thing is we have a bunch of other registers in here. We've used accumulator A for everything we did here, but we can easily switch to B. Our first instruction would become load accumulator B, and instead of being immediate, i.e. loading a constant, we can tell it to load from memory location 10. So most of these instructions that have an A as the fourth letter in the mnemonic, not most, all of them exist for both A and B. And then of course we have 16-bit registers. Just to give you a taste, we can increment the X register, which is also called the index register, and that would look like this. Increment X. And the interesting thing about that, of course, is that it's a 16-bit register, so it will actually do it will operate on the X as a 16-bit number. And in this case, the way we can still do a branch not equal or a branch on plus or whatever after this, but instead of looking at bit 7, starting from 0 of course, it will look at bit 15 in 16-bit registers to set the condition codes. And I guess you all deserve a break today, or you deserve a break right now, so take a break and then we'll go and fire up the simulator that you had a brief glance of in the last episode. Well, we've gotten close to the end of this class. The bell is about to ring, but we should have a minute or two left to briefly go through the family tree of the early 6800 series. Well, you've already seen the 6800. Many variants of this were made, and probably the most prominent ones were the 6802, and what they did on the 6802 is they gave it internal 128 bytes of memory, and also it no longer requires a biphase clock, but rather you give it a single clock input from a single crystal, and it generates the non-overlapping clock inside. That was the difference between this. So they were more going towards an embedded type processor, even though this was still, the 6802 was still a long way off. They also made the 6808, which was essentially a 6802 that wouldn't pass the RAM test on the assembly line. So those chips had one pin assigned to enabling the onboard RAM, and obviously in order to run a 6808 you had to disable the onboard RAM. But I bet you if you have a lot of patience and a lot of time, you can probably get some 6808s and enable the onboard RAM, and you'll find a couple of them that work. Maybe not too reliably, but it would still be an interesting experiment. After the 6800 came the 6809. It was still an 8-bit processor, but it had a greatly enhanced instruction set, ran at faster clock speed, and this was used in quite a few computers. One of the more famous ones was the Radio Shack color computer series. A standard operating systems for these was created called OS 9. Both of these were used in many pinball machines. But obviously, you know, the 8-bit line had to come to an end. So next, Motorola came out with this guy, the 68000. It was a 16-bit processor, which means the data bus was 16 bits wide. It was most prominently used in early Macs, Macintosh computers, and lots of other things. They were obviously fighting the 8086 from Intel, but we all know who won that battle. Nonetheless, they still made a lot of these chips. Maybe we'll get to a point where if we're still interested after finding out all about the 6800, we'll do a series on the 68000 because it has got one of the nicest instruction sets, one of the nicest machine code or assembly language mnemonics that I have encountered. Now, similar to what Intel did, the 8086 was a 16-bit part, but there were people out there who wanted the power of a 16-bit processor, but they didn't want to incur the expense of having to go to 16-bit wide memory. So what Intel created was the 8088, which was basically an 8086 with an 8-bit data path. Motorola didn't want to be left behind, and they created the 68008, which is essentially a 68000 with an 8-bit data path. And the 68000 was followed up with many upgraded versions of it. 68010 here, which was a more powerful processor and started having memory management units and all that kind of good stuff on chip. And the list goes on and on and on. And again, you can kind of follow the evolution of the 68000 in the different Macintoshes that were released and used subsequent more powerful versions of the 68000 for quite some time. But oh, I hear the bell ringing, so we are done for today. And next time, we will actually run the piece of code that we hand assembled today and be able to observe it in real time. Bye.